We're starting section 3.4. That's rate of change. In the first part is 1 unit change. Then it's kinematics. Then it's gravity. So basically a little bit of applications of the derivative. So let's start. Let's start with remembering what derivative meant to us. So for a function y equal to f of x over an interval a and b, delta y is change in y. It's f of b minus f of a. Let's write here f of b minus f of a. That's f of a. And right there, so that's delta y. Delta x is in change in b in x, and that's the b minus a. And so using this notation, the average rate of change would be delta y over delta x. And you see this notation in physics a lot, and we start using it more. This means that f of b minus f of a over b minus a, just change in y and change in x. Now, the instantaneous rate of change is f prime. At a, it's the delta y over delta x as b approaches a, or delta x goes to 0, basically. Example 1, let A be pi r squared, be the area of a circle of radius r. Compute dA over dr, that's the derivative of A with respect to r, at r equal to 2 centimeter and r equal to 5 centimeter. So how do we take the derivative here? The function is function of r, right? It's a of r, and that is pi r squared. This is a constant coefficient. Pi is the constant coefficient. So when I take the derivative with respect to r, constant coefficient stays. Derivative of r squared with respect to r is 2r. The other way of writing it is 2 pi r. Now you plug in 2 centimeter, so if I plug in dA dr and I plug in r equal to 2, I get 4 pi. Then if I plug in r equal to 5, I get 10 pi. Okay, so what does this explain? It's just rate of change at r equal to 2 is a lot smaller than r equal to 5. What does this tell you? We're trying to figure out why is the change in when r is equal to 2, change in the area when r is equal to 2 is so different from change in area when r is equal to 5. And so remember the notation that we just discussed. And this basically, the derivative is the limit of delta A over delta R, right? And so the derivative, I can write this as dA dr is limit, limit as delta r goes to 0 of delta A over delta R. And so let's try to imagine at r equal to 2, this is 2, whatever change, delta R change, it makes a little ring down here, right? Now if I have R equal to 5 and the same with delta R, it makes this type of change. And that's explained. So that would be 10 pi. This one would be 4 pi. Radius 2, the little change delta R is going to make a small area change. At radius 5, little change delta R, the same little change delta R will create a bigger area change. That's the area that is going to be different, basically. If you increase the radius delta R at radius 5, it's much more area added. If you increase the radius by delta R at R equal to 2, you have added a smaller amount of area. The other way of discussing this is that the area function pi r squared is actually a parabola. You see, constant times r squared. And so the parabola is not the slope to the tangent line in parabola over here is not as steep as the slope of as tangent line over there. So the slope of this one is smaller than slope of that one, which are the derivative. Now that we discussed this, let's discuss a change by unit. And this we've discussed in section 3.1 and 3.2 once. It's just representation of derivative. Assuming the derivative exists for small values of h, it's not a representation of derivative. So the effects of a 1 unit change. Assuming the derivative exists for small values of h, the difference quotient is close to the derivative itself. And a lot of times this can be useful. We've used this before. And so the interesting part of this is if we assume h is equal to 1, and then this difference quotient is going to give us f of a plus 1 minus f of a over 1. That is f of a plus 1 minus f of a. And so when is this basically something that we can assume, or something that we should assume, when the quantities are basically not quite continuous, but we are assuming that there's so many of them that they're continuously changing. And so, for example, if you're counting your production of this many items, the production of this many items is not completely continuous. You just count them. So there is no numbers in between, but basically what you end up with is when production is so many, the difference between each two numbers becomes smaller and smaller in the charts, and until you can't see them very much. And so this is a good basically approximation in those type of cases, and we've done this before in exactly production examples, and so that's something that you might do. So using f prime of a to estimate change, the value of f prime is an estimate of the change in f of x as x changes from a to a plus 1. Now, example 1. For speeds s between 30 miles per hour and 70 miles per hour, the stopping distance of a car after the brakes are applied is modeled by the function f of s equal to 1.1s plus 0.05 s squared feet. Estimate the additional stopping distance required for a car traveling at 61 miles per hour as opposed to 60 miles per hour. So numbers are kind of bigger, and we can basically use the estimation from a to a plus 1. And instead of carrying out maybe more complicated derivative to plug in values, we just use the instead of calculating the exact values, we can use the less complicated derivative to estimate the differences. See, in here, if I want to find the actual value, I have to plug in 60 miles per hour in for S, and then I have to plug in 61 miles per hour for S, and then subtract. Let's say you are basically an investigator that are investigating if a car was driving too fast from the skid marks, and you don't have a calculator on you. So it's easier if I can actually approximate this difference. Instead of plugging 61 and 60 and then subtracting, and just have a smaller linear equation that does all of that for me, basically. And so it's the approximation still kind of holds, even though it's not a really big number. So how do we do that? First, you take the derivative f prime, and f prime of s is 1.1 plus 0.1 s. How does that work? 1.1 times s, 1.1 is the constant coefficient stays. Derivative of s with respect to s is 1. 0.05 is constant coefficient. Derivative of s squared with respect to s is 2s, and that's what you get. And then so if you calculate f prime at 60, it gives you 7.1. If you plug in 60 in here, which is compared to plugging these two in there and subtracting, it's a lot easier. You get 7.1 feet per miles per hour. And so the skid mark, if you approximately increases by 7.1 feet per miles per hour, after you increase the speed from 60 to 61 miles per hour. And so this is an easier one for the investigator on the site to actually decide, well, was that the speed 60 or was it 61? And sometimes it's not 60 and 61. Somebody's supposed to go at 40 miles per hour and they're going 80 miles per hour, or all that investigator has to show is that it's a lot more than 30 miles per hour. And so that's the, if you use the calculator actually, you do the subtraction, you get 7.15 feet. So the estimation wasn't too bad. And so there are specific cases, the estimation is a little better, and specific cases, the estimations are worse. But every basically a lot of people who have to calculate things fast, they know in their profession if they can use this estimations or not. And then later on there are other estimations that are given to you in calculus 2 that you can do as well.